We're going to finish out chapter 10. So we're going to start by talking about, like mins and maxes and ranges. For these polar functions. So let's just take a look at some examples here. So if I say I have the polar function r is equal to 3 plus cosine theta, the only part of this r that's variable is the cosine theta part, right? Think back to first semester. What are the possible outputs for cosine theta? Well, 1 is the maximum output. Yeah, -1 to 1, right? So if we want the maximum value, then for r, we want the maximum value for cosine, since I have r is 3 plus cosine. So just 4. Everybody cool with that? Like super straightforward, right? Just had to remember the range for cosine. Okay, what if I, instead of asking for maxes and mins, we ask for a range? Does this really fundamentally change the problem at all? No, still like it basically the same thing. Since it's a range, I'm just concerned about the maximum minimum values of r. And again, I noticed that r is completely controlled by sine theta. That's the only variable part of r. Just like cosine, the range of outputs for sine is just -1 to 1. So my possible outputs for r are going to be 7 and 1, or the extrema for r are going to be 7 and 1. So my range then is just the interval from 1 to 7. Minimum to maximum. Mr. Kulik, that is some easy stuff right there, right? Indeed. Okay, the next thing we'll talk about here are symmetries. So with polar function, there's 3 types of symmetries. There's symmetry with respect to the x-axis, symmetry with respect to the y-axis, and then there's a rotational symmetry. We call that alpha point rotational symmetry. So to prove that something has x-axis symmetry, we're just going to take our r and theta in the equation and replace it with r and negative theta, and see if we can then simplify our equation down so that it's the same thing as what we started with. And the same thing then for y-axis symmetry or alpha point symmetry. So let's do an example here. So here we're asked to prove that the function r equals 5 sine 3 theta has y-axis and 120-degree point symmetries. So to do this, I'm going to take my original function, and because we're looking for y-axis symmetries, I'm going to replace my r with -r and my theta with negative theta. So far, so good. I know that 3 times negative theta is just going to be -3 theta. And if we take a look here, again, what are we trying to do? trying to end up back at r equals 5 sine theta, right? So I want to look at that sine of negative 3 theta. What can I do with that? That's exactly right. That was one of our identities from first semester. That was one of the odd-even identities. That sine of negative theta is negative sine theta. And then if I divide both sides by negative 1, I got back to what we wanted, or what we started with, I should say. So we're done. Great. To prove that we have 120-degree point symmetry, I'm going to just be taking my r and theta and replacing them with r and then theta plus 120. That. So I know that I can distribute the 3. I have 3 theta plus 360. And what can I do with sine of 3 theta plus 360? I have an identity for this. That's an angle sum identity. So the sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. Okay, so let's do that. So I have sine 3 theta cosine 360 plus, oops, need that bracket there. Cosine 3 theta sine 360. Now, I notice here that cosine 360 and sine 360, that's just a number, right? If I go to my unit circle, cosine 360 is 1, and sine 360 is not 1, 0. Which means this whole piece cancels out, and I'm left with just 5 sine 3 theta, which is what we're supposed to end up with. Is everybody okay with that?
What was the first thing you did?
I use. Oh, okay. You're good? Okay. Okay, that's that. Then we're going to talk about, there's 2 types of graphs for polar functions that we're going to talk about. Oops, that's not where I wanted that to land. The first one, or the first type, is called a rose curve. So a rose curve is just something where we have r equals a cosine theta, or r equals a times sine n theta, and n just has to be a positive integer. So if I think about this 5 sine 3 theta here, that guy was should be a rose curve, right? Let's take a look at what that would look like. Oh, look at that. It looks like a pretty little flower. That's why we call it a rose curve. So the domain for any rose curve is going to be all real numbers, because the domain and range, or the domain for sine or cosine, is also all real numbers. The range for a rose curve is going to be negative the absolute value of that a, comma, positive the absolute value of the a, because again, the minimum maximum values are going to be dictated from the sine or cosine, which could be -1 or +1. The maximum value is just the absolute value of A. The number of petals is n. So notice that we had sine of 3 theta, n was 3, and we got 3 petals. And then our last thing is our symmetry. We can actually determine symmetries of Rose curves without actually proving anything. We can just use the rules that we've written down here. So if n is even, we have all 3 types of symmetry. And I'll make that a 6 or something. Right? Symmetric across the x, across the y, and if I rotate like 1 petal, it's the same thing, right? Okay. If n is odd and we have the cosine, we have x-axis symmetry and alpha point. And if n is odd and we have the sine, then we have y-axis symmetry and we have alpha point. Notice that we have alpha point for everything, which hopefully should make sense because we just can rotate a petal and we end up with the same picture. All right, let's do a quick example of this. So to analyze this graph, well, let's just take a quick peek at what it looks like here. So -6 cosine 5 theta. So there's my picture. I know that the domain is going to be all real numbers for any Rose curve. The range is going to be from -6 to +6. I know the maximum value is going to be +6. I know the number of petals should be 5 because n is 5. And then because n is odd and we have a cosine function, I should have x-axis and alpha point symmetry. But I would want to say what is alpha? What angle is alpha going to be? Well, look at the picture here. Clearly, if I spin the picture 360 degrees, it's going to be the same thing, right? But also if I spin 1 petal, so if I spin from like this petal and I move that petal to here, that'll be the same picture also, right? So I just need to figure out how many degrees is it from 1 petal to the other petal. Well, how many petals do I have? 5, and they're all equally spaced. And it's 360 degrees for the whole thing, so it's going to be 360 divided by 5. It's okay. Sure it is, because you're just taking like the center. It doesn't matter if you start like 72 degrees from the back of the petal to the back of the other one, or the front of the petal to the front, or the middle of it. Like it's all the same.
I thought it was kind of space between petals.
Oh, no. I'm saying from one petal to the other petal. Is that okay?
Yes.
So here we'd say, actually, call that 72 degree point symmetry. But that's easy, right? Anything complicated so far? Not really, right? All we've done is like used some rules. Not a big deal. All right. There's a second type of polar graph that we're going to care about. These are called Limousin curves. Notice the word Limousin has that funny C with the squiggly on it, that little C with a tail. I forget what that symbol is called. Anybody remember? Nobody in 5th hour knew what it was called. No? Nobody with like Eastern European ancestry that knows what those things are called. That looks like an Eastern European symbol, doesn't it? Nobody knows? I don't either. Maybe we can Google it later. So, again, the form for a Limousin curve is going to be A plus or minus B cosine theta, or A plus or minus B sine theta. But those A's and B's are always going to be considered positive values. So even if I had like 3 minus 5 cosine theta, the A is 3 and the B is 5. If I had 3 plus 5 cosine theta, A is still 3, B is still 5. Everybody's good with that? Okay. Domain, not surprisingly, still all real numbers. The range is going to be A minus B and then A plus B. Again, because the maximum value for sine or cosine is 1 and negative 1. The maximum value for R is A plus B. And then there's 4 different shapes of Limousin curves we can have. So they are dependent on the size of A and B. So let's just kind of give you some examples of what this might look like. So if A divided by B is less than 1, that means that A has to be smaller than B. And I'm going to do this real quick. I'm going to turn the axes off my graph so it's going to be easier to see what's going on here. So that's an inner loop. You see how there's like a little loop on the inside? That didn't turn out very well. Let's make that maybe, let's do that 2 and 4. It'll be maybe a little bit better looking. There we go. Okay, inner loop. A cardioid is where A and B are the same, because A over B has to be 1, so I'll just make that 4 and 4. Kind of looks like a heart or a butt. If A over B is between 1 and 2, then it's dimpled. So what, like 6 for A and 4 for B is like 1.5. That looks good. So there's my dimple right there. Still kind of looks like the cardioid. Those are the 2 hardest ones to tell apart just from looking at the picture. That's why this is nice, where you can just, look at the value of A and B. And the last one is convex. So A over B has to be bigger than or equal to 2. So if 8 and 4 should work. Oh, didn't go far enough over, but this is called convex. What do we notice here about this guy? Is that there's no indents on this, right? It's all convex. Make you still get convex. It'll just be bigger. Oops. Yeah, sure. So it's just going to be off the screen now. Let's try just doing a zoom fit real quick. Still basically the same convex shape. It's just big. Like the window here is negative 16 to 24. Just it got big. That's all. Still the same general shape though. Cool. And then the symmetry is easy. Cosine is symmetry to x. Sine is symmetry with the y, which matches up really nicely with what we know about sine and cosine on the unit circle, where cosine is x and sine is y. We got one example here, and then we are done with math for today. Sound like a good deal? Feels like I kept my promise. We've motored through this pretty quick. It wasn't too complicated. All right, so if we want to analyze this, let's see. I'd start by just identifying that A is 4 and B is 3. So I know that the domain here is all real numbers. The range is A minus B, that's 1, to A plus B, that's 7. 4 over 3 is between 1 and 2. So this will be dimpled limazan. Our max R was 7. What else is on the list there? Oh, then we have symmetry. Because it's a sine, we know we're symmetric about the y-axis. And that's kind of all she wrote. What do you guys think? Nothing real complicated going on here. So at this point, you guys should be able to do now 85 to 96. So for this weekend, that's the 19th. What do we have assigned? We have like 63 or something. Something like that. Let's double check here. $62. It was 49 to 62. We almost tacked in some extra problems there. And then for next week, that's what, the 26th, we'll have 63 to 96. We'll put all those problems into next week's that we've done this week. That was what 5th hour wanted to do. I said, okay, I don't care. Everybody happy? Good, I am too. I'm done.